Picture this. You're sitting in a spacecraft heading to Alpha Centauri, our nearest star system, and instead of the 70,000 years it would take with today's technology, you arrive in just 20 years. Sound like science fiction? Well, quantum computing might just make this dream a reality sooner than you think. What if I told you that the same technology that could crack every password on Earth in minutes might also hold the key to traveling between stars? Today, we're diving deep into the fascinating world where quantum physics meets space exploration. And trust me, by the end of this video, you'll understand why NASA and SpaceX are quietly investing billions into quantum research. But first, let's address the elephant in the room. When most people hear quantum computing, their eyes glaze over faster than a donut shop window. But here's the thing. You don't need a PhD in physics to understand how this revolutionary technology could literally propel us to the stars. I'm going to break it down in the simplest terms possible, and I promise, no complex equations in sight. So what exactly is quantum computing, and why should you care? Think of your current computer like a really fast librarian. When you ask it a question, it has to go through books one by one, checking each page systematically until it finds the answer. It's incredibly fast, but it's still doing things in order, step by step. Now imagine a magical librarian who could read every single book in the library simultaneously, compare all the information at once, and give you the perfect answer in a fraction of the time. That's essentially what a quantum computer does. But instead of books, it's processing information using the weird and wonderful properties of quantum mechanics. Here's where it gets really interesting. Regular computers use bits, tiny switches that are either on or off, representing ones and zeros. But quantum computers use something called quantum bits, or qubits. These qubits can be on, off, or amazingly, both at the same time. It's like having a coin that's spinning in the air. Until it lands, it's both heads and tails simultaneously. This superposition, as scientists call it, allows quantum computers to explore millions of possible solutions to a problem all at once. When you're dealing with the mind-boggling complexity of interstellar travel, this parallel processing power becomes absolutely crucial. But let's get real for a moment. Interstellar travel isn't just about building a bigger rocket. The challenges we face are so monumentally complex that even our most powerful supercomputers today would need thousands of years to solve them. We're talking about calculating trajectories through gravitational fields that change constantly, optimizing fuel consumption across journeys lasting decades, and navigating through space environments we've never encountered. Consider this. When you drive to the grocery store, your GPS calculates the best route based on current traffic, road conditions, and distance. Simple enough, right? Now imagine trying to navigate to a star that's moving through space. While you're also moving, the solar system is moving, and there are countless gravitational influences from planets, asteroids, and other celestial bodies all affecting your path. Oh, and did I mention this journey will take decades? So you need to predict where everything will be years in advance. This is where quantum computing's superpower really shines. While a classical computer might spend centuries calculating the optimal trajectory for an interstellar mission, a quantum computer could potentially solve this problem in hours or days. It can simultaneously consider millions of possible paths, account for gravitational changes over time, and optimize for fuel efficiency, travel time, and safety all at once. But trajectory calculation is just the beginning. Let's talk about propulsion systems, because this is where things get really exciting. Currently, our fastest spacecraft would take over 70,000 years to reach the nearest star. That's not exactly practical for human exploration. We need revolutionary propulsion technologies, and quantum computing could be the key to developing them. One of the most promising concepts is the fusion rocket. Nuclear fusion, the same process that powers the sun, could theoretically propel a spacecraft to a significant fraction of light speed. But here's the catch. fusion is incredibly complex. You're essentially trying to create and control a miniature star inside your spacecraft. The plasma temperatures reach hundreds of millions of degrees. Magnetic fields must be precisely controlled, and the fuel injection must be perfectly timed. The calculations required to optimize a fusion rocket are so complex that they're currently beyond our computational capabilities. We're talking about modeling the behavior of millions of particles, each interacting with electromagnetic fields that change millions of times per second. Quantum computers could potentially simulate these interactions in real time, allowing us to design fusion rockets that are actually controllable and efficient. Even more exciting is the possibility of quantum computers helping us develop entirely new propulsion concepts. What about manipulating space-time itself? Einstein's theories suggest that space and time are like a flexible fabric that can be stretched and compressed. If we could understand how to manipulate this fabric, we might achieve faster-than-light travel without actually exceeding the speed of light. This isn't pure fantasy. Scientists are already researching concepts like the Alcubierre drive, which would create a bubble of compressed spacetime around a spacecraft. The ship itself wouldn't move faster than light, but spacetime around it would be warped in such a way that it could effectively travel vast distances in very short times. The mathematical complexity of such a system is staggering, requiring calculations that push the boundaries of what's theoretically possible. Quantum computers might be the only way to solve these equations and determine if such exotic propulsion systems are actually feasible. They could help us understand how to generate the exotic matter required, how to control the space-time distortions, and how to make the entire system stable and safe for human passengers. Now, let's talk about artificial intelligence and autonomous systems, because any interstellar mission will require unprecedented levels of automation. Think about it. You can't exactly call mission control for help. We are 5 light years from Earth. Any message would take 5 years to reach Earth, and another 5 years for a response to come back. By that time, whatever problem you are facing would have long since become critical. This means interstellar spacecraft will need artificial intelligence, systems smart enough to handle any conceivable problem independently. They'll need to diagnose and repair complex systems, make critical decisions about course corrections, manage life support systems for decades, and even handle emergency situations that mission planners never anticipated. Current AI systems, impressive as they are, aren't nearly sophisticated enough for this challenge. But quantum computing could change everything. Quantum-ized systems could potentially process information in ways that mirror human intuition and creativity. They could consider vast numbers of possibilities simultaneously, learn from incredibly complex patterns, and make decisions based on incomplete or uncertain information. Imagine an AI system that could instantly analyze thousands of potential solutions to a life support failure, consider the long-term implications of each repair strategy, and implement the optimal solution while simultaneously planning contingencies for future problems. This level of artificial intelligence might only be possible with the parallel processing power of quantum computers. But here's something most people don't consider: communication. How do you stay in touch with an interstellar mission? Radio waves travel at light speed, which sounds fast until you realize it takes over 4 years for a signal to reach the nearest star. Traditional communication with an interstellar mission would be essentially impossible for any real-time coordination. Enter quantum entanglement, one of the most mysterious and potentially useful properties of quantum mechanics. When two particles become entangled, measuring one instantly affects the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance, and he wasn't entirely comfortable with it. While we can't yet use quantum entanglement for faster-than-light communication, the physics doesn't quite work that way. Quantum computing research is revealing new possibilities for quantum communication networks. These might enable new forms of information transfer that could maintain some connection with interstellar missions. even across vast cosmic distances. Quantum computers could also revolutionize how we approach mission planning and resource management. Interstellar missions will require unprecedented efficiency. You can't exactly stop at a gas station halfway to Alpha Centauri. Every gram of fuel, every component, every supply must be perfectly optimized for the journey ahead. Classical computers can optimize for a few variables at a time, but interstellar missions involve thousands of interconnected factors. Fuel efficiency affects travel time, which affects life support requirements, which affects the size and mass of the spacecraft, which affects fuel requirements. It's an incredibly complex web of interdependencies. Quantum computers could potentially optimize all these factors simultaneously, finding solutions that human planners and classical computers might never discover. They could identify optimal spacecraft designs that balance speed, safety, resource requirements, and mission objectives in ways we can't currently imagine. Let's also consider the scientific potential. The whole point of interstellar travel isn't just to say we did it. It's to explore, to learn, to expand our understanding of the universe. Interstellar missions will encounter environments and phenomena we've never studied up close. They'll need to conduct complex scientific analysis using automated equipment, process vast amounts of data, and make critical decisions about where to focus their limited research resources. Quantum computers could enable spacecraft to conduct scientific analysis that rivals or exceeds what entire teams of human scientists could accomplish on Earth. They could analyze atmospheric compositions in real time, identify potentially habitable worlds, search for signs of life, and even conduct physics experiments in the unique environments found between stars. But let's address the obvious question. When will this actually happen? Quantum computing is still in its early stages. Current quantum computers are incredibly delicate machines that require temperatures colder than outer space and perfect isolation from any outside interference. They're more like laboratory curiosities than practical tools. However, the progress has been exponential. Just 10 years ago, quantum computers with a few dozen qubits were cutting-edge research projects. Today, companies like IBM, Google, and others are developing quantum systems with hundreds of qubits. Many experts predict that practical quantum computers, ones that can solve real-world problems better than classical computers, will emerge within the next decade. For interstellar travel applications, we're probably looking at a timeline of 20 to 30 years before quantum computing reaches the level needed for the complex calculations we've discussed. This actually aligns well with other developments in space technology. Fusion rocket research is advancing rapidly. Our understanding of interstellar space is growing through missions like Voyager and soon-to-be-launched interstellar probes. And space agencies worldwide are beginning serious planning for interstellar missions. The convergence of these technologies could create a perfect storm of capability sometime in the 2040s or 2050s. By then, we might have quantum computers powerful enough to design fusion rockets, AI systems sophisticated enough to manage interstellar missions autonomously, and spacecraft materials advanced enough to survive decades-long journeys through interstellar space. Of course, there are still enormous challenges ahead. Quantum computers are notoriously fragile and error-prone. They require perfect conditions to function, and even tiny disturbances can corrupt their calculations. Developing quantum computers that are robust enough for space applications will require breakthrough. Advances in quantum error correction and fault-tolerant quantum computing. There's also the question of power requirements. Current quantum computers require enormous amounts of energy to maintain their supercold operating temperatures and complex control systems. Spacecraft power systems will need revolutionary improvements to support quantum computing in the harsh environment of space. But here's the exciting part. These challenges are driving innovations that extend far beyond space travel. Quantum computing research is advancing our understanding of fundamental physics, leading to new materials with unprecedented properties, and creating technologies that will transform everything from medicine to cybersecurity. The quantum computers we develop for interstellar travel might also revolutionize climate modeling, drug discovery, financial analysis, and artificial intelligence here on Earth. We're not just investing in space exploration. We're investing in technologies that could solve some of humanity's most pressing challenges. Looking even further ahead, successful interstellar missions could establish humanity as a truly multistellar species. The quantum computers that enable our first interstellar journeys could also help us establish permanent colonies around other stars, creating self-sustaining human civilizations that ensure our species' long-term survival. These quantum systems could help terraform planets, manage complex ecological systems on alien worlds, and maintain communication networks spanning multiple star systems. They could enable us to build a galactic civilization connected by quantum communication, networks and powered by fusion reactors designed through quantum simulation. The implications extend beyond just human expansion. Quantum computers could help us search for and communicate with alien civilizations. They could decode complex signals from space, analyze the atmospheres of distant planets for signs of life, and even help us develop technologies for interstellar diplomacy if we're lucky enough to encounter other intelligent species. But perhaps most importantly, the development of quantum computing for interstellar travel represents humanity at its best. We're taking our most advanced scientific knowledge and applying it to our grandest ambitions. We're solving problems that seemed impossible just decades ago and preparing to take our first steps into the galaxy. This isn't just about technology. It's about human curiosity, determination, and our refusal to accept limits. The same drive that led our ancestors to cross oceans and explore continents is now pushing us to develop quantum computers that could carry us to the stars. So where does this leave us today? While we're still years away from quantum-powered interstellar missions, the foundation is being built right now. Quantum computing research is accelerating. Space agencies are developing interstellar mission concepts, and the fusion of these technologies is creating possibilities that seemed like pure fantasy just a generation ago. The next time you look up at the night sky, remember that those distant points of light might not be as unreachable as they seem. Quantum computing is opening a pathway to the stars, and we might be the generation that takes humanity's first steps into the galaxy. The journey of 1,000 light years begins with a single quantum calculation, and that calculation is happening right now in laboratories around the world. The revolution in interstellar travel won't happen overnight, but when it does, quantum computing will be the engine that powers our leap from a single planet species to citizens of the galaxy. And that's a future worth computing for.